Hey, Dr. Clark back with you again, and we're going to do a couple examples for flux surface integrals in this video. Remember, the main idea is you've got a surface integral, you're integrating some function on the surface, but that function is coming from the flux through a surface. So we take a vector field dotted with the normal vector, that dot product gives you a quantity, just a number. That's like a function f that we're integrating. But remember that normal vector, we've bundled that together with the dA here because ds includes the stretch factor of the dA, and this vector here is parallel to the normal vector but not equal to the normal vector. It includes the stretch factor. Okay, but the key concept here is you've got some surfacey kind of thing. There's your normal vector. There's your vector field, right? Maybe f is, who knows what f's doing. But when you do f dotted with the normal vector, you get a quantity of how much sort of flux is coming out through the surface at that point. And then the integral adds up all those fluxes and gives you the total flux. Okay, so the first example, we get a vector field f here, x squared comma 2 comma 3y. And the surface is x minus x squared sine of y. And that's above the rectangle 0, 1, 0 to pi. So in the xy plane, you've got 1 pi here, right? So you've got this rectangle in xy, but in 3 dimensions, right, there's some sort of surface above that rectangle given by this function. And now we want to know for that vector field f, how much of f is coming, through the surface at each point on the surface. And the way that works is you take a little patch of square there, a little dA, that gets stretched into a little ds. And so when we do f dotted with n ds, that's your flux times the however much area you've got, and then the integral adds those all up to get the total flux. Okay, let's actually do the problem. So we've got a double integral over the surface of f dotted with n ds. That's equal to integrating over the region below. The region below is x's from 0 to 1, y's from 0 to pi of the vector field x squared comma 2 comma 3y dotted with, and now we need to know what that normal vector is. So the normal vector comes from g, which is the function x minus x squared sine of y. And so gx, the x partial derivative, would be 1 minus 2x sine of y. And gy, the y partial derivative, would be x minus x squared cosine of y. So what we want is negative gx, so that's going to be 2x minus 1. That's negative of 1 minus 2x sine of y. And then negative gy, well, that'll be x squared minus x cosine of y, and then 1, so we get that upward normal vector. And then we got to do that dx dy. Okay, so dot producting those together, we're going to get what? 2x cubed minus x squared sine of y plus 2 x squared minus x cosine of y plus 3y dx dy. And now it's really just a double integral that we have to evaluate using our standard methods of calculus. So we're integrating the x's first. Let's do that. So antiderivatives all around. We've got x to the 4 over 2 minus x cubed over 3 sine of y plus 2 x cubed over 3 minus x squared over 2 cosine of y plus 3y squared. Plus 3yx. X is evaluated from 0 to 1 dy. If we plug in 0 for x, we're going to get 0 for everything. But if we plug in 1, we're going to get what? A half minus a third is a sixth sine of y. And a third minus a half would be negative a sixth. So 2 times a negative 1/6 cosine of y plus 3y dy. All right, and now we integrate the y's. 0 to pi, 1/6 of cosine of y, that's negative. The antiderivative sign is negative cosine. Minus 1/3 sine of y plus 3y squared over 2, evaluated from 0 to pi. I don't know why I wrote the integral again. We're taking the antiderivative. And that gives us what? Negative 1/6 cosine of pi, which is negative 1, minus 1/3 sine of pi, that's 0, plus 3 pi squared over 2. And then we need to subtract negative 1/6 cosine of 0, which is 1, minus 1/3 of 0 plus 0. So I think what we end up with is what? 1/6 plus 3 pi squared over 2 plus 1/6. So that's 1/2/6, which is really 1/3 plus 3 pi squared over 2. So that's the flux through that surface, and that's how you do that problem. Let's take a look at the next one. Now this one's interesting. We're going to actually tackle this two different ways. One by thinking about it, and then one by doing the actual calculus. So we've got this radial vector field xyz that's going through the sphere, x squared plus y squared plus z squared equals 1. That's the unit sphere, okay? That's the sphere centered at 0, 0, 0 of radius 1. And what's interesting is the normal vector is just xyz, because xyz, x squared plus y squared plus z squared equals 1, that is a unit normal vector. So if we wanted to actually do the surface integral f dotted with n ds, in this problem we can actually do it, because we know on that surface the vector field is xyz and the normal vector is xyz. And that gives us integral of s of x squared plus y squared plus z squared ds. But we're on the sphere where x squared plus y squared plus z squared is 1, which means we're getting just the one function integrated over the sphere. And if you integrate the one function on a sphere with a surface measure, you're just going to get the surface area of the sphere. And the surface area of a sphere is 4 pi r squared, but that's just 4 pi for a sphere of radius 1. So you can do this one just by using your knowledge of geometry and the definition of what a surface integral is, because for a sphere, we know that the unit outward normal vector is xyz. All right, but that's not what you came here for. You wanted to see it done with the calculus. Okay. So I will oblige you. Just remember we got that 4 pi, but otherwise, let me just erase all this and we'll start over and we'll actually do it the way you wanted it done, thinking about it with the calculus and the formulas and that kind of thing. Okay. So we want the double integral on the surface of the vector field dotted with n ds. Okay. And we're going to integrate over the surface. What is that? xyz. And we're dotting it with nds. So what is that? Well, in this case, there's actually going to be the top of the sphere and the bottom of the sphere. So I'm only going to do the top of the sphere. So the final answer will have to do the bottom of the sphere too and add them together. Okay, so for the top of the sphere, the function is z equals 1 minus x squared minus y squared all square rooted. That's our g function. So our gx is going to be negative 2x over 2 root 1 minus x squared minus y squared. And our gy is going to be negative 2y over 2 root 1 minus x squared minus y squared. That's just taking the derivatives. And so, let me just slide this down a little bit. So when we do the dot product, we're going to get negative gx. So that's just going to be x over root 1 minus x squared minus y squared. negative gy, so that's going to be y over root 1 minus x squared minus y squared, and then 1 dA. Okay, so now we've swapped out the surface for the shadow lands under the surface, this region R down here, dA, because remember we've packaged up the stretch factor in there. When we do this dot product, we integrate over the region R. We're going to get x squared plus y squared. We do that dot product. They're over a common denominator, 1 minus x squared minus y squared, plus z, and z is 1 minus x squared minus y squared, dA now. Okay, now this is a sphere, that's a circle down there, so yes, you guessed it, we're going to hot swap this into polar coordinates. So theta is going to be 0 to 2 pi, r is going to be 0 to 1 because it's the unit circle from the unit sphere. And then what do we have? We have r squared over 1 minus r squared plus, sorry, the square root of 1 minus r squared plus the square root of 1 minus r squared, r dr d theta. Okay? And now, this one's a little bit more work than you might expect it usually to be, because we're going to have to do a u substitution. U equals 1 minus r squared. So du is negative 2r dr. So I don't have, whoa, I don't have a negative 2r dr. Now I do, but I'd have to divide by negative 2 on the outside. And that's going to give me now 1 over negative 2, integral 0 to 2 pi. U's are going to be from 1 to 0, because if r is 0, then 1 minus 0 is 1. And if r is 1, then 1 minus 1 is 0. So the u's go from 0 to 1. And my integral turns into, well, this is just root u down here. And then that's a root u there. This 2r dr here, that negative 2r dr, is du. So that turns into du d theta. But what is this nonsense? This is an r squared right here. Well, r squared, that looks to be 1 minus u, right? If you solve that for r squared. So I actually get 1 minus u here. And that can be handled. It's just a little extra work. So I got negative 1/2, 0 to 2 pi, 1 to 0, 1 over root u, minus root u, because u over root u is just root u, but it's minus. And then I've got plus root u. Well, that actually is pretty good because those cancel out. Du d theta. Okay, so now it's time to actually do the problem here. Antiderivative of 1 over root u is u to the 1/2 to u to the 1/2. Okay, and that's going to be evaluated from 1 to 0 d theta. And that's going to give us, when you plug in 0, you're going to get 0, 0 minus 2, I guess, d theta. So now I got negative 1/2 times negative 2 times theta from 0 to 2 pi, and that gives me 2 pi, I guess, 2 pi. But that was only the flux out the top, right? So there's 2 pi out the top. There's going to be 2 pi out the bottom as well, and that's a total of 4 pi, which is what we had when we did it the other way. Okay, so that's kind of a nice problem as well. You can work it out on the bottom as if you want, but because it's an outward flux, you'd want to use, gx, gy, negative 1 as your normal vector dA package deal, because you'd want the downward vector, not the upward vector. So that's one thing to keep in mind. Hopefully you found that helpful, and we'll see you in the next video.